And so this will be available to people if you want to see it. It's my pleasure to welcome Jim Kuykendall. So he's an old friend of mine. He was an undergrad at Caltech, did his graduate work at Cornell. And so he spent 17 years at North Dakota State University in Fargo, and is presently professor at Clemson University, South Carolina. He's probably the expert on unique factorization for all sorts of domains. And so Jim today is going to tell us about exploring some pathologies in factorization via some examples. So without further ado.
Thank you, Mike. And thanks to you all for showing up. I'm glad to see folks here. I'm going to talk a little bit about factorization. I do, my PhD was actually number theory. And so I do commutative algebra now. And really a lot of the commutative algebra I do is on the borderline of number theory, things that kind of look like algebraic number theory. And so if you look at, so commutative rings with one, what sets this apart really in algebra? Well, this is just an abelian group, right? And the only thing different about it is the fact that you have multiplication. So some kind of multiplication thrown in. So in a certain sense, when you talk about factorization, you're talking about the way that things decompose multiplicatively, right? And that's the thing that sets us apart from just studying ordinary abelian groups. In fact, any abelian group can be made into a ring, maybe not with one, by just declaring that the product of any two elements is zero. And factorization actually basically has got its hands in everything that is commutative ring theory, right? It's got its hands in factorization is integral in module theory. It was essential in the work of Fermat's last theorem, for example, and multiplicative ideal theory. So here are the ground rules. So when I say the word ring, I mean commutative with one, and I'll usually mean no non-zero zero divisors, except at the end of the top. And what I mean by that is in my little playground here, if A times B equals zero, then either A is zero or B is zero, right? So none of this funny stuff. And I'm also going to talk about monoids. So how many of you are familiar with what a monoid is? Well, maybe not everybody. So commutative, cancellative, and usually reduced. So I'm going to give you an example that I hope will sort of encapsulate all these words here. Let me give you an example of a monoid. Monoid, I think of this as just, it's got one operation, mono, right? So consider z minus zero under the operation multiplication, right? So this is everything except zero. Notice under the operation of multiplication, what happens if you multiply two non-zero integers? You get a non-zero integer, right? So it's closed under that. It's commutative because it doesn't matter what order you multiply integers in, right? It's the same answer. It's cancellative because if you have AB equals AC, then B equals C, right? Because you don't have a zero in there to worry about. And this one's not reduced, right? So if I wrote this monoid out, if I'm looking at the multiplicative structure of this, basically what I'm doing is I'm doing the old hat where, you know, you take an integer and you multiply it into its primes, right? There's really no difference between this and between the negative side and the positive side, right? It's just that pesky minus sign. And so usually we consider an equivalence relation where we mod out by the units, right? So instead of considering this whole monoid, I might just consider 1, 2, 3, 4 under multiplication, right? And notice that this is a monoid. This is the unit element of monoid. And this one actually decomposes nicely, right? That's the fundamental theorem of arithmetic, right? That every integer 2 or greater can be written uniquely as a private prime. Now you all have all heard that one, right? So I will sometimes write my monoids additively. Give an example that I'm going to come back to. Here's a monoid. This is one of my favorite ones, and I'm going to use this to illustrate some stuff. This monoid is the natural numbers under addition with 0 thrown in for good measure. This is a monoid because it's closed under addition, right? It's actually cancelative, additively cancelative. So if A plus B equals A plus C, then B equals C. And this one's actually reduced because the only unit element is this. I might talk about factorization here, but now I'm talking about it additively. How can I decompose 6? I can compose it in either of these two ways. And the magic thing about 2 and 3 is they are what I'm going to call irreducible, right? You can't break 2 down any further in this monoid. You can't decompose it into smaller things. You can't decompose 3 additively into smaller things, but everything here and higher you can, right? And so notice that you have a factorization additively here of 6. And in fact, everything in there is a sum of 2s and 6s if you want. When I say a monoid is reduced, that means that the largest subgroup of the monoid is the identity. Okay. So when we talk about factorization, I'm going to talk two things. I'm going to talk in a ring where you've got a ring like the integers, where you've got 2 things going on. You've got addition and you've got multiplication. Those are the big operations there. Factorization studies the way things decompose multiplication. In a monoid, it's the way things decompose with only the one operation that I have there. So important in this is the notion irreducible, prime, and unit. These are 3 important notions, right? We say pi, and I'm not going to specify whether this is a ring or a monoid because the definition is essentially the same, is irreducible. Well, actually, what I need to do first, let me get this straight. I was going to say unit before I said unit. We say U is a unit if there exists V such that UV is the identity.
Welcome back, and I'm going to go ahead and share my screen.
So if we look at
On the
the
tablet wall.
integers, the only integer that is a unit, the only integers that are unit are 1 and -1, right? Because yes, it's true, there is a number that you can multiply 2 by to get 1, the identity. However, that number is not an integer, right? In a monoid, in a reduced monoid, the only unit up here is 0, right? Because the identity is 0, and the only thing that you can add to that to get the identity is 0 itself. We say pi is irreducible if pi can be decomposed into two things in my structure, be it a monoid or a domain, then A or B is a unit. Right? Irreducible means you can't break things down in an interesting way, right? Anytime you factor it, one of those factors has to be something that's invertible. Right. So for example, I can take 6 in the ordinary integers and break that down into 2 times 3. That's interesting. But 2 I can't break down any further because no matter how I factor it, 2 is -2 times -1. One of those pieces is invertible. And we say pi in a domain, I'm not going to talk about primes and monoids here, is prime if pi divides AB as pi divides A or pi divides B. So how many of you all have heard the terminology irreducible or prime? You heard that in your travels, right? In the integers, these are almost synonymous. There's actually a prime integer that's not irreducible. Anybody know what it is? 0 is actually prime in the integers, but it's not irreducible. However, every irreducible integer is in fact prime. How many of you know that these are actually distinct concepts? Anybody know of an example that splits them up? Let me throw you all an example here. This is one of my favorites, and this example will come up later. So let's look at primes versus irreducibles and domains. In the ordinary integers, if you forget about zero, in the ordinary integers, the notion of prime and irreducible are the same. In the integers, you've also got the fundamental theorem of arithmetic. Y'all remember this one, right? That every integer greater than or equal to 2 can be written uniquely as primes, right? Well, in that setting, these two are synonymous, but they can be different. So let's look at example. Look at the set of complex numbers of this form. I'm not going to give you a proof. And by the way, in this talk, I'm not going to give, I might peek under the hood a little bit, but I'm not going to give anything hardcore and concrete unless you come bother me after the talk. I'd be happy to talk about it. I just want to give you all kind of a feeling for stuff here. Let me point out, this is kind of a classic example. The 6 is 2 times 3. Can you believe you guys showed up for a talk where that's going to be a big reveal right there? But hey, you're the one that made the mistake. Anybody see a more interesting way to factor this? This also factors in 6. And so it turns out that all of these elements here are irreducible. You can use a norm argument if you like, or you can just get on your horse and ride and try to factor 2 into 2 elements that look like this and come to some contradictions. But these 4 things are all irreducible. However, none of them are prime, because notice the 2 divides the product of these 2, but it certainly doesn't divide either one of these, right? Let me give you an example that is perhaps a little bit easier to see or to visualize. This is one of my favorite examples. Pick your favorite field, any field, it could be the real numbers, whatever you like. And look at this ring. Now I'm going to have to tell you what I mean by this. This is the set of all polynomials of the form where the coefficients are in the field. So basically, these are polynomials that are missing the linear term. They have zero linear. Notice that this is a ring, because if you add two polynomials missing the linear term, you don't magically get a linear term out of it, right? And if you multiply two polynomials that are missing a linear term, it will still be missing a linear term. But it's easier to see some examples of irreducibles that are not prime and to verify. Notice that x squared is irreducible. Because after all, how can you factor it? The only non-trivial way to factor x squared is to break it down into 2 degree 1 polynomials, right? And there ain't no degree 1 polynomials. I've cheated you out of them, right? And how about x cubed? Well, 3 is bigger than 2, but you still got the same problem. If you want to factor non-trivially, you need a degree 1 factor, and there ain't one to give. So these two things, in fact, are irreducible, but they're not prime. Right? Notice, of course, here's an irreducible factorization of x to the 6. Here's an irreducible factorization of x to the 6. Notice that x squared divides these two, but it doesn't divide either one because there is no x, right? So this is perhaps an easier way to see a good example of something that happens to be irreducible, so you can't break it down any further, but it is actually not prime. You might have noticed some similarities in this example with this particular monoid that I had put up here before, and that's not a coincidence, actually. So any questions so far? Okay, so when looking at factorizations in integral domains, so maybe the most basic factorization type domains, UFDs are king. Well, are royalty. How about that? How many of you have ever heard of UFDs? Maybe not. That means unique factorization domain. That's the bad part about community knowledge. There's too many letter things going on. But anyway, this means a unique factorization domain. What does this mean? These are the kind of integral domains where you have the fundamental theorem of arithmetic, just like you do in C. So that is to say, every element that is not 0 and not a unit can be factored uniquely into prime elements, right? So UFDs, synonymously, that means these are the places where you have something like the fundamental theorem of arithmetic. So, for example, any polynomial ring over a field, Rx, complex numbers X, QX, any field, formal power series. For those number theory fans out there, the Gaussian integers, the ordinary integers, they're all over the place. All of these things have the fundamental theorem of arithmetic. A field has the fundamental theorem of arithmetic trivially because there are no non-zero non-units, as a matter of fact. But let's dial it back. Here's the most basic factorization type. If you're going to talk about the way things decompose multiplicatively, the first question to ask is, can I factor it? Right? So we say R is atomic if each non-zero non-unit of R is a product of atoms. and atoms are synonymous with irreducibles. So that's the reason that they're called atomic, is everything can be written as a product of atoms, which are irreducible. So atomic domains are the type where everything can be factored. So if you take an element, then you can find a way to factor it into irreducible elements, right? Of course, this is true for everything where you have unique factorization, right? Now, I guess the question is, what kind of rings are atomic? And my answer to that would be probably most rings that you encounter in a first abstract algebra course or in a lot of applications, right? Does anybody know what an Ethereum ring is? In commutative algebra, this is a very central part. So it means all the ideals are finitely generated. If you don't know what that means, it doesn't matter. But all Noetherian rings, which are a big subject to study, they're all atomic. I guess the most basic question I could ask is, can anybody think of a ring, commutative ring with identity, no zero value, where there's something that you cannot factor into a product of irreducibles? Sometimes seeing the non-examples. Good. Here's one. What do I mean by this construction right here? What I mean by this is polynomials with rational coefficients, right? Everybody comfortable with that? Just any polynomial that has fractions for its coefficients, right? But I'm going to make one slight rule adjustment. And that is my constant term must be an integer, right? I can have 1/2 multiplying x, 1/3 multiplying x to the 5th, whatever, but the constant term has to be an integer. Now notice, if the constant term can be any rational number, it falls in this category. You have the fundamental theorem of arithmetic. Now, there are elements here that cannot be factored into irreducibles. Anybody see one? Anybody see an element that can't be factored into irreducibles? I'm going to make you mad. X cannot be factored into irreducibles. And you say, Jim, are you high? Of course. I mean, isn't it irreducible itself? Right? But it's not in this ring. And here's why. I can do this, correct? Now, this thing in this ring is actually, in fact, this 2 is actually prime. This thing is not irreducible. And I can keep pulling this out. And in fact, it's fairly easy to prove that no matter what's left over, the degree 1 part that is left over always has another factor that can be pulled out. Why can I do this here, but I can't do it if I allow all rationals here? Well, the difference is this thing is not a unit here, but if this was a Q, then this would be a unit, and this factorization is meaningless, right? So it's kind of a cheap trick in a way, right? But this is an example of a ring that is not atomic. And it's kind of mixed in the sense that some things can't be factored into irreducibles and some things can. Can anybody, I'm gonna up the voltage. I'm going to give you an example of a ring that's not atomic, that has no irreducibles whatsoever. So no matter what you pick up off the ground, it factors. right? Like, for example, in this ring two, it's irreducible. There aren't going to be any here. This ring, the set of complex numbers such that Z is a root of a monic polynomial this is often called the ring of all algebraic integers. It's very big, but still countable. So for example, every integer is in here because every integer, take your favorite integer n, it's the root of x minus n. But it's got more exotic stuff, right? The square root of 2 is in here, right? Because it's the root of x squared minus 2. And the cube root of 2 is in there, it's x cubed minus 2. And in fact, all 5 complex roots of x to the 5th plus 2x plus 14, those are all in there, right? This is a big, messy ring. Let me give you a quick proof. I told you I'm going to get up under the hood. I'm not going to be super careful about this. There are no irreducibles in here. Let me give you a short proof. Assume that alpha is an irreducible. Alpha is the square root of alpha times the square root of alpha. And it's easy to prove that if anything is in here, then its square root is also in there. So no matter, everything is a pile of sand. Whatever you pick up starts to fall apart in your hands. This has no irreducibles at all. Okay. So those are negative examples. Positive examples. Noetherian rings. I should say domains here. All ideals finitely generated. Any integral domain that's the homomorphic image of a polynomial ring over a field or Z and finite many variables will be atomic as well. Here's another large class. For those of you that have seen the definition of Noetherian, Noetherian means that every ideal is finitely generated. It also means that every ascending chain of ideals must eventually stabilize, right? You can't keep going up forever. ACCP implies atomic. Okay, I told you there were too many abbreviations in this crap, but ACCP means the ascending chain condition on principal ideals, right? So what it means to be ACCP is if you have a principal ideal or a chain of principal ideals that's ascending, it eventually must stabilize. So anything that has this, so this is actually a weaker condition. Noetherian means all ideals stabilize. ACCP just means, maybe all ideals will stabilize, but it's the principal ones. For many years, it was thought that these were equivalent. In fact, there's a very famous mistake, actually, that persevered for years in the literature, that atomic was equivalent to the ascending chain condition on principal ideals. And this was actually resolved by one of my heroes, Emmy Noether. No, I'm sorry, she actually corrected something else. This one was actually corrected by Anne Graham's later. And I'm going to give you an example of this. So let me try to, as best I can, give you an intuitive feeling for this. What does it mean to be atomic? It means if I walk up to you and give you something, you can find some irreducibles to factor that are factors of this, and you factor in those irreducibles, right? ACCP means if you start with anything and you just go up, you will eventually stabilize, right? ACCP is atomic for idiots, right? What that means is if you start with something and you pull a factor out of it, it doesn't matter how you pull the factors out, you're eventually going to stop. Atomic means maybe I've got to be careful about how I pick those factors. Because if I choose the wrong path, I might keep going forever, but there is some way that I can make this stop. There is an example written in monoid form by Grams. Who actually wrote some wonderful papers. I'm going to give you this example. And I'm going to couch this in terms of monoids. And this will sort of connect with the examples that we've got coming up. Consider the following monoid. And this is an additive submonoid of the rational numbers. So 1/6 is one of my generators. And 1/20th So what I'm going to do is I'm going to additively generate using these particular fractions. 1/6, 1/20th, 1/56, and so forth and so on. Right? My pattern is increasingly large powers of 2 in the denominator, and p to the n is the nth odd prime. Right? So the next one will be 1 to the 2 to the 5th over 13. Right? Everybody okay with it? This is actually an atomic monoid because these things are all irreducible, right? You cannot decompose this into a sum of these smaller things. That's fairly easy to show, actually, because remember, the decomposition here has to be over the natural numbers. So it's a little bit grungy, but you can show that these things actually are all irreducible and they generate everything in there. So it's atomic because everything can be written as a product, or in this case, a sum of atoms. But it's not ACCP. It doesn't have the ascending chain condition because of the fact I've got this. If I add it to itself 3 times, I have 1/2. Correct? Because of the fact that I've got this, if I add it to itself 5 times, I've got 1/4, which contains this. Because I've got this, if I add it to itself 7 times, I have 1/8. And so forth. So even though everything in here can be written, decomposed as a finite sum of these atoms here, inside there's an ascending chain. There's an ascending chain of these principal ideals. 1/2 is contained in this because 2 of these is this. This is contained in this because 2 of these is this, and so forth and so on. It's a terribly clever example. Now that's just for monoids. Is this true also for domains? And this is kind of a standard trick. This is also true for domains. And this is kind of, maybe you'll see that earlier connection when I did the monoid 0, 2, 3, 4, 5. Now look at that other ring here. Here's what you do. So what I mean by this notation here is this is like polynomials, right? So a typical element here will be alpha I x. These alpha i's are in the field, whatever this field is, but the m's actually come from the monoid. In this monoid here, I'll call it M here. So think of this as all possible polynomials, loosely speaking, that are allowed to have those exponents. I can have an exponent of 1/6. I can have an exponent of 1/20th and 1/56 and so forth, right? And it turns out that the theme of this increasing chain here captured in the monoid, you also get this here. This turns out to be an atomic ring, and it turns out to also, in fact, as you might guess, the corresponding ascending chain is this. Actually, I started at the wrong place. X 1/2, X 1/4, X 1/8, etc. So you translate the factorization of the monoid into the factorization of the domain just by building a polynomial ring with the exponents coming out of that monoid. Often this works, and it's always pretty much a good approach. And it begs the following question. Most of my examples have been for rings. And so this one I said, okay, this works here for monoids, and look, it works for monoids, and we pass it over here to domains, so good for us, right? So why don't you consider only monoids, right? A lot of factorization theories started out looking at integral domains, and then there's a large school of people in Europe that actually look at just factorization in monoids, right? Should solve the problem, but it doesn't. The problem is, in general, that you've got a little bit too much freedom for monoids, and some things some things pass over nicely, like that previous example. Some things are a little bit less friendly, and you lose some of the nice results that you might want if you're looking at rings. Let me give you an example here. So here's an example, which I might call monoids versus domains. And here's some hazards. Okay. Okay, earlier I talked about UFDs, and these are places where you have fundamental theorem of arithmetic. So what does it mean to be a UFD? So I'm not going to be super careful about this, but I'm going to say given two irreducible factorizations, alpha 1, alpha 2, alpha n equals beta 1, beta 2, beta m. Suppose I could factor some element into a product of alphas. These are all irreducible. And suppose I could do it some other way, into a product of betas, also irreducible. If it's a UFD, you got two things going on. If this is going to be a unique factorization, those links better be the same, right? First and foremost. And two, we can pair off once the links are the same. So that is to say that after reordering, alpha 1 and beta 1 are essentially the same up to units. Alpha 2 and beta 2 are essentially the same, and so forth, right? That's what it means to be a UFD. So unfortunately, people in community algebra have a bad sense of humor. There's also the notion half factorial domain. And this is given two irreducible factorizations. Then n equals m. So maybe factorizations aren't unique, but all the factorizations have the same length, right? I'll give you an example of my earlier example, C6. Remember how we had 2 times 3 is 1 plus radical negative 5, 1 minus radical negative 5? It turns out that every factorization in that ring has that property, right? That you might have different factorizations, but they're always the same length. 2 times 3, there's 2 factors. 1 plus radical negative 5, 1 minus, 2 factors. And this is even worse. Other half factorial. What this means is given alpha 1 alpha n equals beta 1 beta n. Notice now I'm assuming the links are already the same. Then you can pair off. So other half What that terminology means is if two factorizations have the same length and are equal, they're the same, right? So we got two different concepts going on, sort of this half and that half. Do these things exist in nature? Yes. Let me give you an example of, let me give you the monoid. Let me give you the monoid side of this. Let's do a half factorial domains just from the point of view of monoids. Let me give you a monoid here. I've already given it to you. This one is, oh, no, it's not. That's the other one. Look at the monoid generated by x squared, xy, and y squared. Just those symbols, right? Notice that, for example, x squared times xy squared is xy quantity squared. Notice that x squared, y squared, and xy are all irreducible. 1, 2 factorizations, 1, 2 factorizations. And you can play with this. Anything in here is just a product of x squared, y squareds, and xy, right? And you can do a little bit of computation and convince yourself that all factorizations have the same length, even though they may be different. These are two different factorizations, but they have the same length. Agree? If you look at this monoid, which we saw earlier, this is another half. Notice that this is not a half factorial monoid because 2 plus 2 plus 2 is 3 plus 3. We saw that earlier. So notice 6 has 3 factors this way and 2 factors that way, if you think of it additively. However, if you have 2 factorizations of the same length, so suppose you have 2 factorizations of the same element. So you have n copies of 2 plus m copies of 3, because actually those are the only 2 irreducibles in that monoid. And you have k factors of 2 and l factors of 3. And you want the lengths to be the same. So you also have n plus m equals k plus l. This is the equation that tells you the lengths are exactly the same. This implies, and you can, I mean, I'll multiply this by 2, subtract, and you can go to town. You get n equals k and m equals l. So it's unique. So this is actually an other half factorial monoid. Here is a theorem that shows the pathology and the hazards here. HFDs for domains, HFDs that are not UFDs exist in abundance. So for example, C adjoined with square root of -5, Z adjoined with square root of -3. If you have any field F inside K, then F plus X KX is an HFD and not a UFD if F is strictly contained inside K. So for domains, these exist in abundance. However, if R is atomic and an OHFD, then R is a UFD. This is actually, I think, kind of an interesting theorem because what it says is, even though I can build these things that don't have unique factorization in monoids, it is actually impossible to build this with an integral domain if you assume that the integral domain is atomic in the first place. Right? So that is kind of pathology number one that I think is kind of strange. And it illustrates that working with monoids is actually very useful, but care must be taken. Here is another pathology. If equals if you look at this monoid here, M is atomic, not ACCP. Right. However, and again, however, this fails with two variables. So if you look at F X M cross M, this monoid is actually still has the same property. It's still atomic, but not ACCP. So this is essentially the same as taking polynomials in two variables. Both exponents now come out of M, right? That's another problem. And now, before I go, I'm going to tell you about the worst one. So, with zero divisors, this is worse when you want to talk about factorization. Let me give you sort of an example of how bad. Remember how we get that example where X wasn't irreducible because I could keep factoring stuff out of it, right? This, in a sense, is worse. This angers up the blood a little bit, right? Because in Z6, if you look at the quadratic term, it's multiple 6, so it's gone. And if you look at the constant term, it's multiple 6, so it's gone. And the middle term is 4 plus 9, which mod 6 is 1. So X actually factors this way, which is really nasty. But it gets worse. So example, I'll give you a quick example. Let R be, let's see, do I want, yeah, I'll just do the field of two elements. So Z2, if you like. And what I mean by this is the alpha i's can be in. So here's what I'm going to do. I am going to build this original domain R by taking the field of two elements, and I'm going to adjoin infinitely many polynomial variables, right? But I'm going to let the exponents come from the positive rationals. Everybody okay so far? Now let I be the ideal generated by X alpha 1, or let's say X beta 1. X beta K alpha K, where alpha 1 plus alpha 2 plus alpha K is greater than 1. So basically what I'm doing is I'm taking every possible monomial that has degree 1 or higher, right? And that is when I add all the exponents up. Now, if you look at R mod I, basically, intuitively, a typical element of this looks like a sum alpha I xi, where xi is a monomial composed of this and its degree is less than 1. Notice that these are all nilpotents because if you take a big enough power of this, it's going to be 0 because eventually its power is going to exceed 1 and it's going to be 0, right? This thing has no irreducibles at all because everything has a square root, right? Everything's got a square root in this, right? So there are no irreducibles at all. You take anything, it's got a square root, you're hosed. You can't find any irreducibles. However, and this is when I swore off zero divisors. If you take this ring and look at its polynomial ring, is atomic. And in fact, you can look at a polynomial and bound certain factorizations. So even though the coefficient ring, you can't factor anything into irreducibles, everything, including the constants in the polynomial ring, factor into irreducibles. Because even though this thing might have a square root, you can build a degree 2 polynomial or a degree 1 polynomial, 2 of them, to multiply together and get this, and the degree 1s will be irreducible. And that's, yeah, that's when I stopped. Okay. That is, I think, enough. I've brushed some broad strokes. Does anybody have any questions? Yes, sir.
Earlier,
Uh-huh.
by x squared, xy, y squared
Uh-huh.
versus x squared, x cubed.
Mhm.
They behave differently. Is that because each of them is a quotient of a polynomial ring by a principal ideal, but in the former, it's
Let me make sure that I'm.
by a homogeneous polynomial. The other one is not homogeneous.
Let me make sure that I'm on the page that I need to be on. So were you looking at,
X squared, xy, y squared.
right, and I just generated this as a monoid, right?
So like, if the range generated by them is the range generated by, let's say, capital X, capital Y, capital Z, with XC equal to Y squared.
So you capital X, capital Y, capital Z, with what now?
The ideal is in mod XZ minus Y squared. That's a homogeneous.
Oh, so are you asking if this is an HFD or?
This is the first example here. The second one is the range generated by x squared and the x
Oh,
cubed
right. So like this one.
is the range generated by that is f x y capital X capital Y modulo x capital X cubed minus y squared, which is not one.
Right. This one actually automatically has to fail to be a UFD because it's not integral closed. Right. And that's a big problem with this one. This one, I didn't really pay attention to the ring. I only used this as a monoid. And I did this multiplicatively. This is sort of isomorphic to the monoid. This is actually the monoid. You can think of it this way as generated by, this is a submonoid of N cross, well, let me say N0 cross N0. Generated by 2, 0, 1, 1 and 0, 2. Right, exactly. And so this one actually has the half factorial property, and this one doesn't. And actually, this monoid, the monoid by itself has the other half factorial property, but this domain fails to be other half because actually, if you look at this in this ring, whoops. So these are both irreducible. This is x squared times x squared plus 2x cubed plus x4, I think. And so these are two equal length factorizations that are not the same in this ring. So even though the monoid generated by the monomials actually is OHFD, the ring isn't. And the way I cheated there is I added things up, which you can't do in a monoid.
My question was maybe because one is the quotient by a principal ideal of a homogeneous polynomial, the other is.
Well, again, I wasn't looking at this as a quotient of anything. This wasn't a ring. I just used the symbols to generate the monoid. But yeah, I mean, if you want to talk about, there's been some work on, like, you know, if you quotient out by something, you know, what conditions on the ideal will make certain things happen. And actually, I get really cautious about saying anything on the fly, very carefully about that, because weird things can happen. So.
And second, bird was an example of a weird example.
Yeah.
You said nothing fact can be factored. Irreducible. Something cannot.
Everything in this ring actually is either a unit or a nilpotent, right? And so the units don't matter. Everything else is a nilpotent, and the nilpotents are just sums of these monomials that you make. And every one of them, because we're in characteristic 2, actually, every one of them has a square root. And so there's no irreducible whatsoever. Actually, you can actually massage this into any characteristic P, and you can also massage it into characteristic C. So there's an analog that works in characteristic 0. But yes, in this ring, there's only units and nilpotents, and all the nilpotents except for 0, all the nilpotents can be factored down into something smaller. Any other questions?
Yes, here.
Yes.
In the definition of M, the sequencing of prime was not important, right?
Right here? The same?
Yeah, the sequencing of prime 2, 3, 5, 7, whatever you had. Any infinite sequence of prime will be okay, right? Or no?
Yeah. Sure, you could do that. Yeah.
So maybe it's just because I don't know enough about the subject, but like, you know, when you talk about Euclidean domains, right, you have a norm function and, you know, we use, you know, whether it's degree or just absolute
Right.
value, or whatever. It seems like there's like an underlying like linear order.
Mhm.
So if you're just talking about posets, you know, so if you have like incomparable, like how does that, is that playing some sort of role that we don't understand about?
Yeah, and in fact, that's one of the things with looking at simple examples makes it easier for, if you look at the monoids that I constructed, almost all of them were comparable, except this one wasn't totally ordered, but like a lot of them are comparable. The real difficulty sometimes is the addition, right? Because really what's happened here is now, you know, you don't have x squared dividing this anymore. And yeah, so when the sum creeps in, you get these kind of weird things that happen, and it can be complicated.
Questions? Thank you.
Well, thank you all very much for having me, and you all stayed awake too. I mean, I could barely do it, so that's pretty impressive.